Well, ladies and gentlemen, I want to welcome you back to another exciting chemistry video. I'm super excited today to bring you Unit 3. Our focus today is going to be on solutions and mixtures. So our primary focus is going to be on utilizing the concept of molarity, which is how we measure the concentration of a solution, and utilizing that as a conversion factor in a variety of different stoichiometry problems. In addition to that, we're also going to look at properties of mixtures and how we can separate mixtures into their individual constituent components. I'm really excited today. I hope you're excited as well. Excited enough to leave a like and subscribe to the channel. So let's go ahead and get started. Our focus today is going to be able to describe solutions on a microscopic level for solids, liquids, and gases. Yes, solutions are not just aqueous. We need to be able to calculate and solve for molarity, calculate a dilution, look at particle representations of solutions, and then correctly separate mixtures using either chromatography or distillation, and then describe what types of solutions are miscible and immiscible. So lots of things we're going to cover today. Let's get started. So at the very beginning here, what I want to focus on is just the concept of solutions, and solutions are just homogeneous mixtures where different components of the mixture cannot be discerned. Now, there is a difference between a heterogeneous mixture and a homogeneous mixture. We're primarily going to focus on the homogeneous mixture. Those particles are distributed uniformly. So again, it doesn't necessarily have to be an aqueous solution. So for example, vodka here is about 40% alcohol. Don't ask me why I know that. But a lot of vodka is just water. And so it is a homogeneous mixture because you can't discern the alcohol from the water. Steel is another example of that. Steel is a homogeneous mixture of iron and carbon. You can't discern the individual iron and carbon atoms as a part of that. Now, solution concentration is commonly expressed using molarity, which is just simply your moles of solute divided by liters of solution. It's represented by big M. The higher the molarity, the more concentrated the solution is. So for example, something that is 6 molar has a higher concentration than something that is 1 molar. There are more moles in something that's 6 molar than 1 molar. And again, we represent that by the letter M. Now, because it is a derived unit, right? We have moles of solute over liters of solution. I can use that as a conversion factor between grams, moles, liters, milliliters, etc. We can utilize that to convert specifically between moles and liters. So it's a very, very useful tool when looking at things like solution stoichiometry problems. So the basic calculations of the concentration of a solution is relatively easy. Moles of solute divided by liters of solution. You may be given grams, you may be given milliliters. There's a variety of different ways that you can calculate that. But when we're mixing different solutions together to determine the concentration, we need to follow a couple of steps in order to be able to do that. It's not as simple as just plugging in a couple of numbers and solving. We have to do a couple of extra steps here. So for mixing different solutions together, the key thing is to extract the number of moles of solute of each solution, because then we can add those together and then divide by the total volume of the new solution. So it does require a couple of extra steps here. Remember that we can even calculate the concentration of ions in a solution by using the mole ratio of the compound to the number of atoms in the compound. For every 1 mole of CaCl2, I have 2 moles of Cl-. It has to do with the number of atoms that are present in the compound and using that as a mole-to-mole ratio. You'll see what I mean here when we look at a sample problem. So let's take some time and determine the concentration of ions of chlorine when 40 milliliters of 2 molar AlCl3 is added to 20 milliliters of 1 molar CaCl2. So we need to find two things here to find the concentration: the total number of moles of chlorine ions that are in these two solutions and the total volume of the solution. Well, the volume's easy. I have 40 milliliters and 20 milliliters, so my total volume is going to be 60 milliliters or 0.06 liters. Now, to get the moles out of this, we're going to have to do some stoichiometry in order to be able to solve for that. We never start with a derived unit, so for each of these, we're going to start with a number of milliliters. We're going to then convert milliliters to liters, liters to moles, utilizing the molarity, and then mole of compound to mole of ion in the compound. So if you look there for AlCl3, for every 1 mole of AlCl3, I'm going to have 3 moles of chlorine ions. So I do my stoichiometric calculations for both of them, and notice how they're very similar. We just use the different concentrations that are given to us in the problem, and then we use the different mole ratios of compound to ion in order to be able to determine the total number of moles of chlorine in each individual solution. We're going to add them together to get 0.28. We then divide that by our liters of solution. So we have a new concentration of 0.467 molar. It's all about breaking this problem down into individual steps. Find the number of chloride ions for each individual solution and add them together. Then divide by the total number of liters of the entire solution to get the new molarity. So let's talk about making a solution. This is an important lab practice here. So when we make a solution, the best way is to always use a volumetric flask. Now, volumetric flasks look a little bit different than maybe the flasks that you've used previously. These flasks only have one mark on it, and it's typically in the neck. These flasks are designed to specifically measure one volume of solution only. Typically, it's 50, 100, 250, 500 milliliters. But it's much more accurate than using, say, a beaker, Erlenmeyer flask, or even a graduated cylinder. In order to do this, though, we have to follow two important steps. First, we add our solute. You always add your solute first, and then add your solvent until the desired volume of solution is reached. If we added our solute after we added, let's say in the very top one there, we added 100 milliliters of our solvent and then added our solute, our total volume of solution is going to be greater than that of 100 milliliters, and therefore the concentration is not going to be accurate. So it is important to make sure that we're following these steps in the exact order. Adding your solute first, then fill up with solvent until the desired volume of your solution is reached. So when we make dilutions of compounds, we're going to have to utilize a simple formula. Now, I use this quite frequently in lab to make your solutions. It's a very simple calculation. M1V1 equals M2V2. So let's say I know the initial concentration of the material I'm looking to dilute, and then I know the desired concentration and desired volume of what I want at the end. I'm going to know how much of my original material I'm going to use and then dilute that with water to reach the desired volume. So utilizing M1V1 equals M2V2 is a really quick way to determine how much of my initial starting material I need to use and then how much water I need to add in order to get my second volume. So it's a very, very useful tool and a very useful equation when you're going through and figuring out how am I going to go through and dilute these solutions. It's important to be able to appropriately draw diagrams as well. Diagrams can be appropriately represented with particle level diagrams, so it's really important to consider the ratio of the number of ions in solution. Also consider ion dipole intermolecular forces. If we were to draw out diagrams of solutions and it asked for the ion dipole intermolecular forces, we know that the oxygen of water molecules are going to be attracted to the positively charged ions, while the hydrogen of water is going to be attracted to the negatively charged anions that are present in solution. And we know that this is the case due to Coulomb's law. So those are just a couple of things you want to think about as you go through and you draw out particle diagrams of solutions. So again, to reiterate what we've just discussed, based on the concentration of particle diagrams on the left, draw out the appropriate number of ions in the box for CaCl2. Well, we have 8 sodium ions and 8 chlorine ions in the diagram on the left. On the right-hand side, we're looking for calcium chloride, but half the concentration. We also have to keep in mind that for every CaCl2 that dissociates, we're going to get 2 chlorine ions. So because the concentration's in half, rather than having 8 sodium ions, I'm going to have 4 calcium ions that are in solution. And because we have 2 Cl ions for every 1 Ca that dissociates, I'm going to have twice as many Cl ions, so I would draw 8 chlorine ions in that box. So we need to take into consideration not only the concentration of the solution itself, but the ratio at which the ions are going to dissociate when they are put into solution. There are a couple key ways we can separate mixtures as well, and one of these is what is known as paper chromatography. Now, solvents are going to travel up a piece of paper with mixture that is placed at the bottom. Think about like if you get your pants wet when it's raining outside and you notice how the water kind of travels up your jeans, travels up the pants. Well, same way paper chromatography works. The only difference is that like polarities of the solvent and the chemicals in the mixture will travel further than dissimilar polarity solvents. So as a result, we can separate mixtures of different polarities based on utilizing the solvent as well as what type of paper we are using. So for example, if we are using a polar solvent, the molecules that are polar are going to travel further up the filter paper than things that are less polar or non-polar. This is one way we can actually go through and separate mixtures as well as determine what dyes are present in the mixture of different dyes and the mixture of different substances. So it's a very powerful tool. In addition to that, we can use distillation, and distillation separates mixtures based on boiling point. So what you would do is, if you have two compounds with differing boiling points, you're going to set a boiling point in between the two components of the mixture. One of them is going to boil off into a fractionating column, and then once the gas reaches the top of the column, it reaches a condenser. The condenser usually has water that's flowing through it, which cools the gas, thus condensing it back into a liquid. Well, over time, one of the components of the mixture is going to boil off while the other one is going to stay in the original beaker. So as a result, we can utilize distillation as a way to separate mixtures based on their differing boiling points. So again, two ways we can do this. We can look at boiling points, we can look at polarities. Two different ways to separate mixtures. The very last thing I want to take a look at is the solubility of compounds. Now, the way we want to think about this is like dissolves like. That is, materials with similar intermolecular forces and similar polarities are more likely to dissolve in one another than those with differing intermolecular forces or differing polarities. This is why things like oil and water will not mix with one another, because oil is nonpolar and water is polar. So if we're trying to determine if two different chemicals have the ability to dissolve in one another, we just simply need to look at their polarities. If two things are polar, they're more likely to dissolve in each other than something that is polar and something that is nonpolar. Those chemical properties are key to being able to predict whether something is going to be soluble in solution or insoluble in solution. So again, a lot of things that we've talked about and briefly touched on today, but we will certainly go over more details on this as we get to class. So do keep these things in mind. Make sure you're able to describe solutions on a microscopic level, utilize molarity for a variety of different solution calculations, be able to calculate a dilution, show particle representations, separate mixtures, know the difference between miscible and immiscible solutions. Hope you've enjoyed the video. As always, make sure you leave a big thumbs up on that. Have a great day, and we will see you soon. Bye-bye.